Hello, my name is Max Jones, ignore the William, and I'm here today from the Axel Scherer Nanofabrication Group, and I'm here to talk about our integrated nanoscale field emission devices. And I just want to say I'm happy to be doing this Oxford talk. I'm a senior graduate student, and I have used and abused your tools for about 6 years, so I'm happy to meet you all. So to motivate this talk, we are thinking about making electronic devices, and we need to look at the current state of electronic devices and where they operate poorly to see where we have an opportunity. So if we think about modern transistors made out of silicon and solid state, they do poorly at high temperatures, mostly because of shifting in the Fermi level. So this limits silicon devices at 300 degrees Celsius. If you're willing to go to a wide bandgap semiconductor like silicon carbide, which is a whole new set of processing technologies, which I imagine the Oxford people can talk about, you can go as high as 600 C. MOSFET devices also do poorly in high radiation environments. I think this is crystal lattice damage, which destroys lifetime in the channel. And at higher frequencies, possibly. The possibly there is caveated, because maybe we can do better. Where would you find these types of environments? Well, you'd find them in space, and you'd also find them in defense. And that's actually where our funding comes from. We're funded by a combination of Boeing and JPL for high radiation environment and high temperature electronics. I've been told that we're going to the sun, so I think that will be relevant. What? Yeah. So the type of technology that we do is called nanoscale cold field emission. And I'm going to give like a long sort of history lesson because this particular topic has a vast amount of history. So from 1900 to 1950, the type of, well, 1910, the type of device that we used in electronics was the vacuum tube, in case anyone remembers that. A vacuum tube had a vacuum encapsulation. It had a thermionic emitting cathode. That meant that you got a piece of metal really hot, so it boiled off electrons. It had a collector that was biased to suck up those electrons, and then a transparent gate, which was a mesh. And you could apply signal on the gate to turn this switch on or off, or to amplify the current on the signal on the gate between the emitter and the collector. That all kind of went away with the invention of the solid-state transistor. And the solid-state transistor sort of fixed some problems of vacuum tubes. One was that they were fragile because you had to maintain vacuum, and two, they ran hot because you had to heat up this piece of metal, and so it would shoot off electrons. My advisor has a story about fixing an old SEM that somehow had a power board that had 8 or 9 vacuum tubes on it, and he, not being very careful, figured out that one of the vacuum tubes was wrong and replaced it with a vacuum tube that had the same current voltage characteristics but ran a little bit hotter, and then he says he melted the board. I always like that story because, ironically, that's the problem that silicon MOSFETs today face at the 14 or 7 nanometer node. That's why we have a thing called dark silicon, where modern CMOS processors, we cut off part of the transistors to avoid hitting the thermal budget. So anyway, solid-state transistors were invented in, I think, 47, maybe 49, and then they started to take off, becoming eventually integrated circuits and being shrunk and higher quality materials. And a guy named Ken Shoulders at SRI in 1958 saw this burgeoning industry, and he says, aha, we could take these same tools and we could build vacuum tubes but smaller. And if we built them small enough, we can make them work in an utterly different fashion. And the way they would work is, instead of having to get an emitter tip really hot to have it boil off electrons, we would make a field on the emitter tip so strong that it would rip electrons out. And then we'd get rid of our heat problem, right? And he also hypothesized, well, if we could truly make them micron scale or even nanometer scale, we could even get rid of the vacuum. Because he said, well, the mean free path of electrons in atmosphere is 200 nanometers, so if we make them small enough, we don't need vacuum. So we can fix these two problems that they had. And work kind of proceeded along these lines in tandem with the semiconductor industry. As we could shrink devices smaller in semiconductor, we could make smaller vacuum tubes, and they got better and better. And it was an area of a lot of active interest in the early 1990s. And some of you may remember that we used to have display technology based on one giant electron gun, where we deflected the beam across a screen horizontally and vertically, a CRT. I don't know how many of you remember that. So in the early 1990s, people said, well, flat panels are what people want. They want to have a huge screen, but they don't want to have all that throw. And so why don't we just make 1 million electron emitters, and we put them on like a flat screen, and then each pixel will have its own driving electron source. And the technology actually matured quite well. You can see an example right here. I swear I'm smart. You can see an example right here. Something like I think 1,000 of these individual emitting sources. The top layer is a gate, and this was meant to drive a display. Unfortunately, LED LCD technology came about in like 1994, 1995, and was a much better idea. And so the industry kind of died. But we intend to bring it back, but for a different purpose. We're not making displays. I'm going to give a little cartoon definition review of cold field emission, and I hope this goes well. Imagine your electrons in a metal, and you're right at the edge of the metal. You see a barrier to vacuum, and that barrier is usually the work function. At the nanoscale, it's a little bit different than like the bulk work function that you get quoted, usually modified by stuff on the surface. But you see this barrier. Now imagine you bring in another metal, and you apply a voltage between them. You bend the vacuum field. You bend it down. If you were to bring that metal in closer or apply an even stronger field, or if you were to do both, you could bend it down so much that electrons here would see a barrier that they could tunnel across into free space. And they would do so. And then they would proceed down the electric field gradient and smash into the cathode, and then you could collect them. And then you'd have a modern-day vacuum tube. Sans vacuum. To do this, you need fields on the order of a gigavolt per meter. The way you can sort of think about that field is you think about the common work functions of metals. For instance, gold, which we're going to talk about later on, is about 5.1 in bulk. And then you think about the distances that people build for tunnel junctions. It's something between 2 to 5 nanometers or so. And you divide the 5 eV by 2 to 5 nanometers, you get a gigavolt per meter, or a volt per nanometer. That's sort of where that number comes about, although there's a mathematical definition for this, which we'll talk about very briefly. So how do we achieve these high fields? Well, we could take two capacitors. That's not the greatest idea, but we could have a large plate and apply this voltage, and we'd see that the electric field drops uniformly all the way across. That's not a very smart idea because the fields you need are fantastic. What about if we had a very sharp tip and a large collector? Then we'd get most of the field to drop next to the tip for the same voltage. We could maybe get the electric field high enough to cause electrons to come shooting out of the emitter tip. If we were on a higher current, we could put a whole bunch of them next to each other. This is the type of technology that I showed you before. It's actually in use today for ultra-bright electron sources. You have emitter to gate distances of about 5 microns and operating voltages at about 100. Now, the thing this relies on is you having a very sharp emission tip compared to your collector. So people measure radii in the order of like 4 nanometers. And you all have to operate in this like highly enhanced field regime. And it's a little bit unstable. The reason is you have these array of sharp tips. If one of them gets damaged, it automatically stops emitting, and so your high brightness electron source has a noticeable lifetime. Also, Reese is online. So these devices are inherently fragile, and their large emitter to collector distances means that they have to be operated in vacuum. So they're good for high brightness electron sources, maybe wouldn't be good for integrated circuits. So we move to a different regime, and this different regime is where we have a sharpened tip, yes, but we bring it close so that we can operate in this small field enhancement environment. In the regime that we're going to talk about, we get a field enhancement factor of something like 3 to 5 times what you would get if it was just a capacitor separated by the same distance, like parallel plate capacitor. And we think that that's a much more robust regime, and we have found that that's a much more robust regime. Because if the tip experiences damage, there's usually some other part of the tip which can start emitting, experiences about the same field enhancement. So finally, in our review of this thing, we're going to talk about the Fowler-Nordheim equation. So there's math to support this tunneling phenomena. You can get this math if you consider like quantum tunneling over a triangular or a modified triangular barrier. But in general, the equation follows this format. It's dependent on the field strength squared times exponential minus the field, 1 over the field strength. And it kind of looks like this. This is sort of sample data that I ran through MATLAB. This is the current voltage characteristic. And the reason I show you this is because I want to show you this in a different representation. So if you look back at the other equation, you can sort of figure out that if you plot the x-coordinate in 1 over v, and you plot the y-coordinate in I over v squared, you'll get this straight line. So these are called Fowler-Nordheim coordinates. And so the upshot is looking at current voltage characteristics for things at nanoscale gaps. It's hard to figure out if you're dealing with Fowler-Nordheim coordinate, or sorry, a Fowler-Nordheim emission event or some other leakage. But if you put it in these Fowler-Nordheim coordinates and you see a straight line, you can, one, interpret things like the work function of your material, but also be sure that you're not somehow leaking across substrate or leaking someplace else. So when I show you graphs, I'm going to show them to you both in the current voltage characteristic, because that's the one that people understand, and also in these Fowler-Nordheim coordinates to extract some parameters and also verify that we're doing what we think we're doing. Cool. So our objectives are to build a field emission device. And we want it to operate at about CMOS voltages. And we want to make it compatible as much as we can with CMOS fabrication rules. And then we want to test whether it can operate at elevated environments. And we want to test whether it can operate in the exposure of radiation. And then, as I said before, our applications are in space and defense science. Space science and defense. So our initial attempts involved building these suspended silicon structures on SOI. We would cut the smallest gap we could, something like 30 nanometers, and then we'd undercut the entire structure, and then we'd oxidize these tips. And when the tips oxidize, because the silicon dioxide crystal lattice is a little bit bigger than the silicon crystal lattice, our things would become puffy, and they would swell, and they would shrink. Then we would deposit metal in a very non-conformal manner, and we'd end up with this metal layer on top and this other metal layer on top, and we could get incredibly small gaps. Here's a 15.6 nanometer. We even built a 7 nanometer device. I thought this was great, and this is also a NEMS switch, not a field emitter. So when you suspend these devices, you make them able to move under the extremely high electric fields, and they're able to just bridge. And you see sort of switching behavior from these devices. And that will be a theme in my talk. At high fields, basically anything can happen. So we realized that we needed to stay on substrate. And so we're going to stay on substrate. So our current fabrication procedure begins with doped SOI. We dope the top layer in-house. We do E-beam lithography with a cold development process. We use an AL2 hard mask. We use 12 nanometers, basically the smallest we possibly can. We lift off. We use it to transfer the etch in the pseudobosch with the Oxford tools. And then we use photolithography to define contact pads, wet etch, and wet etch of the exposed alumina hard mask to reach the silicon, lift off in solvent after depositing these chrome gold contacts. And the combination of lithography and needing to etch, we get down to about a 22 nanometer size. And we can do this sort of over and over again on devices. I think the 22 nanometers is mostly limited by my lithography. Although there will be a point in this talk where I ask the Oxford people to help me out in a thing. And our device looks like the one down here. Now, this looks like the cartoon I showed you before, with one sharp tip and one blunt tip. So it operates in a semi-field enhanced regime. And the red portion of this graph, you see 0 is right here. The red portion of this graph represents current in the forward direction, as though the emitter is emitting electrons. The dashed portion is the current collected by the collector. The red portion is the current emitted by the emitter. Perhaps opposite, because I think current is minus. The blue portion of this graph is trying to emit current from the blunt side in the opposite direction. Same thing for the dashed and for the solid. You can see that we do get turn on of our diode earlier if we try to emit electrons from the sharp tip than if we try to emit it from the blunt tip. And that kind of makes sense. And like I said before, this is the current voltage graph, and you never know if that's what it is, like if it's truly Fowler-Nordheim emission, until you plot the same thing in Fowler-Nordheim coordinates, which I've done here. So again, the red is emitting current from the sharpened tip. The blue is emitting current from the blunt tip. You can see that you have these straight lines indicating true Fowler-Nordheim emission. I said that you could extract parameters. If you do, you extract something like 4 eV, I think, for these devices, which makes sense. Silicon, bulk silicon is 4.5 eV, if I'm remembering my numbers. And at the nanoscale, that gets slightly modified. At high voltages, which is going this way, you can see that the sharpened tip becomes a little bit unstable. If you read the literature, you end up with the driving theory is that you end up with such high fields at the tip that you start causing atomic motion, although that's kind of outside my purview to investigate. But anyway, the device is repeatable. So we have built this diode. But diodes are not enough. I'm missing a picture here. I don't know why. Simple diode replicas are not enough. We want to make gated devices, and we want to make them integrated on a single wafer. So how are we going to do that? Well, we're going to take our earlier paradigm of a sharpened structure and a blunt tip and in a doped silicon layer, and we're going to have a gate oxide offset. In this case, we're going to use alumina, ALD alumina, and then we're going to have a chrome gate and another chrome gate. So we'll have two gates. The gate over the sharpened tip can modulate the current coming out of the emitter by depleting this thin silicon layer the same way that a gate on a MOSFET depletes the channel. This blunt gate can directly modulate the field at the emitter surface, making a very fast emission process. And all the current will end up going to the doped silicon collector if we can keep this distance small enough. So we built this device. Just checking my time. We begin similarly with this doped SOI. We deposit our AO2 hard layer. We use E-beam lithography, cold development. Because we're dealing with an insulating surface, we use a charge depletion layer. Yeah, anti-charging layer. We deposit a hard mask, which consists of our chrome gate layer and also our alumina hard mask. We have to do a thicker one because we have to cut through more material. We lift off in solvent. We use a CH4Cl2H2 etch to drill through that alumina ALD layer, and then we use a nice reasonable pseudo-Bosch to get all the way through. Because we have to deposit such a thick mask to do the job, we end up with a minimum feature size of about 60 nanometers, and a device that looks like this. You can see the ghost of the layers right here. And the device works, and it gates. So this is the IV characteristic of the device. The red current is the current leaving the emitter. The blue current is the current entering the collector. And then you can see that we get some current in the green. We see the current entering the gate. You can see that we have some gate leakage current. But we do have modulation with increasing voltage on gate 1. It turns out, when we made this device, that gate 2 was partially eaten away, and so it doesn't serve as a modulation. We're making more to try to figure out if we can get that, but this is a thing in a publication, so this is what I'm including. But, as I said before, nothing is anything unless we see it in Fowler-Nordheim coordinates, and we do, in fact, see it in Fowler-Nordheim coordinates. It's straight. This also indicates a reasonable, I think the work function for this indicates 4.5 EV, which means we are emitting from the doped silicon. You can see that the gate slightly changes the y-intercept. The y-intercept in these graphs corresponds to the area of emission. So basically what's happening is as we increase the gate voltage, we're getting a slightly larger area of emission. So that's cool. And as I said before, we should be able to get rid of the vacuum because we're at 60 nanometers, which is much less than the mean free path of electrons in air, which is about 200. And we operate at different pressures. Our device is noisy, so it bounces around. You can see this is 1 e to the minus 2. That's 1.9 e to the minus 4. That's e to the minus 5. So it bounces around a little bit. But each time it's Fowler-Nordheim. We haven't operated at atmosphere, partially because of our testing setup, the way it kind of works. But we predict no problems. So one of the things we said that motivated us was, as you pointed out, the money. And the money comes from people who want to operate at very high temperatures, so we would like to operate at very high temperatures, if we could. When we are on substrate, as we pointed out that we have to be, Fowler-Nordheim competes with surface leakage mechanisms, so the way to be able to operate hotter and hotter is to make that surface leakage harder and harder, and that's cutting into the oxide. So we use dry etching to cut into the silicon oxide. We increase the resistance of this alternative pathway, but because we haven't suspended our structure, we prevent this NEM switch behavior, which perplexed me when I was a third year. That was great. That didn't show up for whatever reason. That didn't translate, but this is increasing temperature for this device. This is Fowler-Nordheim for increasing temperature. The high here is 350 C. The low here is 50 C. You can see that as we increase the temperature, we shift the relative turn-on, but we also increase this like leakage current here. And we wonder if we can sort of parse that out. If we look at the Fowler-Nordheim coordinates, we can see this kind of thing. So in temperature increases going this way, all the way up to 350 C. We can see that at 50 or 60 C, we have straight Fowler-Nordheim, and then we get this kink here. This, we think, is Franco-Poole emission along the oxide that happens before Fowler-Nordheim takes over. If you kind of look at these emission mechanisms, you'll come to the conclusion that Fowler-Nordheim scales faster with voltage than Franco-Poole, but Franco-Poole, this leakage mechanism, scales faster with temperature. So basically, the name of the game, our name of the game, is to cut this leakage pathway as much as possible with an incredibly high aspect ratio or reasonably high aspect ratio DRIE etch into this oxide. So I think this is a 60 nanometer gap, and I think we have 200 nanometers into the silicon and another 300 nanometers into the oxide, thereabouts. So if somebody at Oxford has a great idea for how I can cut even deeper, I would love to talk about that. That would make my day. I also wanted to take the last few minutes and talk about how we're pushing for even smaller gaps. So if we get a gap as small as 10 nanometers, we sort of get outside of this weakly field-enhanced regime, and we get back to the capacitor plates, which I said was not the greatest idea in the world, but it's good for a couple reasons. One, if we're in this sort of capacitor region, we are ultra insensitive to tip damage, because if a part that's emitting gets damaged by maybe an ion that got ionized by our electrons, we have another part right next to it, which is the same distance away, experiences about the same field, and can also start emitting. So you're resilient to tip degradation. Also, because you have this long capacitor plate, you have the potential for more than one emission site. Fowler-Nordheim emission is notoriously noisy, and if you can average over many emission sites, you can get a relatively stable current. In this scheme, we would have two gold layers, gold because of a fabrication region, which I'll talk about, on top of a doped silicon layer, and you would gate this transistor with capacitive-like fringing fields. So if you applied a voltage emitter between the emitter and the collector, you get a field that goes like this. If you now apply a voltage gate, you pull down and also lengthen this field line, and you end up generating more current, but because these two are so close, it goes into the emitter anyway. And I'm sad to say we don't use an Oxford tool to do this. We use a Zeiss tool. We use helium fib milling of this gold surface. We have to worry about our materials because this helium fib swells silicon. I have a nice picture of that. And also because we want as small a distance as possible, in this case we have 14 nanometers, we need to work with thin metallic layers instead of our crystalline silicon. I am losing all the best pictures. I had a cross-section here which showed swelling on my computer. But anyway, I'll show it here. So you'll notice that this region right next to the cut is a different color. One of the reasons this is because as you cut through the gold, you implant helium into the silicon. Helium starts to swell the silicon, and the whole thing kind of rises up like that, which ultimately limits your size because you will swell into each other. But anyway, it's a thing that we're working out right now. Also, dealing with thin metallic layers of gold, we get some really cool things. As I said, our theme of this talk is that at high electric fields, weird stuff happens. So we have this 17 nanometer gap. We then apply an electric field to try to make it field emit, and the gap just closes itself. It's a self-healing device. So gold is particularly soft. One way you can get over this is to try to use a harder metal. We have been trying to increase the grain sizes in our gold by electroannealing. I'm working with a fellow grad student while I do that. But it's a work in progress. We have some early results. I don't want to share them at this point because I'm not yet sure about them. But that's where we are in the Axel Scherer lab. I'd like to acknowledge the entire nanofabrication group. You see right there. Ignore the fact that I'm holding a plunger. I'd like to acknowledge the generous support of the Boeing company and also the staff at the KNI who have helped me so much, especially Matt, who really helped me with this helium fib business. Thank you very much.
Excellent. Some questions? Silence. You can't have coffee yet. You've got to have one more talk. Speak up or wait for the mic.
Just a quick fab question about your thin chromium layers.
Yeah.
So did you have issues with those oxidizing because they're so thin and because you're putting an oxide on top of them?
So we don't try to emit from them. So they work well enough to apply a voltage. So they don't oxidize all the way through, I guess, would be the thing I would say. But I do think they partially oxidize, yes. If we were trying to emit from them, which is the thing that we considered, you really have to worry about oxidation of your tips. When emitting from silicon, silicon oxidizes, but it develops this native oxide layer, and it just presents a larger barrier to tunneling. And so it makes it a little bit harder, but still possible. I don't think chrome self-terminates the way that silicon oxide does, so I think it's more problematic. I wouldn't use it as an emitting material. One of the reasons we're using gold in this other thing, one of the good things about gold, other than to offset the fact that it's so soft a material and it has a relatively high work function, is that it's relatively inert to oxidation. So we can emit and collect pretty easily.
You did throw one out in the middle of your talk saying, if only we could etch deeper. What limits you now? What goes wrong?
So I want to etch deeper, but I want to maintain the smallest emitter-collector gap that I can. I prefer 20 nanometers or less, and I'd prefer to make that trench microns deep, which I think is hard, but I'm not a young grad student. I'm a grad student, so maybe I don't know.
Yeah, all the science in the world is done by grad students.
Yeah.
So if you can't do it, no one else can. There's a definition of a scientist is somebody who can find the leak. And the definition of a senior scientist is somebody who helps the scientist find the leak.
Yeah.
So,
So I think the aspect ratio of this trench.
yes, so what happens, if you just keep going, what do you run out of?
My mask erodes.
You run out of mask. It's
and if I want a
selectivity.
thicker mask, my lithography would limit me to the distances that I can make. So it's really that trade-off.
So it's the selectivity, and the material trying to etch is silicon.
Silicon, and then eventually silicon dioxide. Although, as I was compiling these slides, I had an idea, but we'll ignore that. So right now, it's silicon and silicon dioxide, and I'm using an alumina hard mask to do the whole thing, and
right.
fluorine-based chemistries to get my.
So you're already using concrete as a mask.
Yeah.
And
if you got something better than alumina, like.
Think about that one. No, alumina. You're already using a hard mask. There are other hard masks. Some people use carbon.
Yeah.
But no. Okay.
So it's that aspect ratio that's the deal, and that aspect ratio is formed in part by the need to etch deeply, but also by lithography. I need 3-to-1 ratio, say, between the height of my resist and the layer that I deposit.
Okay, well that should be possible. Let's have a think about that offline. People do etch 10-to-1, 50-to-1 in some instances.
Yeah. So in this case, I think we're about 10-to-1, and I know people etch 50-to-1, even more. I've seen people in my group to etch more than that. I think maybe the specific feature is hard, but I don't know. This is where I'm at, and I would love to hear any comments anyone has.
Okay. I suspect we'd have to look at the details of the mask edge, because a nice sharp mask works wonders, and a rounded mask, you're fighting forever.
Fighting everything, yeah, I know.
Fighting everything. So the etch guy is going to blame the litho guy, as usual. Okay, thank you very much.
All right, thank you.
Have we got Carl Yee? Where are you, Carl?
Thank you.